All right, so first few announcements are over here on the whiteboard. On the homework, your maximum score is 4 points. Attempt every problem legitimately, you will get a score of 4 points. On the top of the homework, many of you write lots and lots of things, and that's fine, write whatever you want, but the only things that I am hoping to find are your last name and the homework number. So if you just put the page numbers, that doesn't help me so much, and if you just put the date, that doesn't help me so much, but the homework number is how I can tell where to put your grade. So homework number and last name. You don't have to put anything else, but put other stuff if you want. Okay, so the quiz thing will come up here as we look at our calendar. So today, Friday, February 6th, happy Friday. Project 1 is officially due right now, although most of you, I think, turned it in Wednesday, which is when it was due before the snow day. You do have a little bit of a break because Project 2 is not going to be assigned until Monday. It is sitting over here on the table, so if you want one, you can grab it at the end of class. So in that break, you're going to do a take-home quiz. And so it says here quiz number 1 is due this coming Monday. So you don't have this quiz yet. It's right here in my hand. So I just want to make clear what the rules are for this quiz, and I will give this quiz to you this period later on. So just like last semester, if you had either Caitlin or I, these are take-home quizzes. You're going to do them individually. It's one of the few things this semester that I ask you to not work with your neighbors or anybody else on. All the rules are specified at the top of the quiz, but I just want to say them so everybody's on the same page. It is not an untimed quiz. There is a recommended time limit on here. This one is a 40-minute quiz. It also says in here you can take up to double the recommended time, so up to 80 minutes, but in theory, it's a 40-minute quiz. At least that's how it was written. It tells you whether or not you can use the calculator. In this case, it's a scientific calculator only, but not a graphing calculator. It also says that you can make a 3x5 index note card with anything you want on it, but you got to do that before you start looking at the questions on the quiz. Okay? One of the common comments that many of you wrote at the end of the last semester with either Caitlin or I on that last project was, gosh, I wish the quizzes were out of some more points because one little mistake and my quiz grade would drop, you know, by like half a letter or something like that. So I'm going to accommodate that this semester, but that means the quizzes are longer. So like this 40 minutes is longer than any of the quizzes you had last semester, and it's because I'm trying to make it so that one little mistake isn't worth as much percentage-wise. Okay? Any questions on the quiz? All right, so like I said, I'll give these out at the end of class today. When you come in, you'll slide them right into the green folders at the start of class. Yeah, Sephora, is there a question? You. So it says up here, I'm taking you on your honor to not cheat. It says right here to write in the start time and then to write in the end time, and then at the back you're going to sign something that says I did not cheat. So but it is on your honor. I would prefer if you just didn't have because it's possible that not everybody knows exactly what functions are on the graphing calculator that aren't on the scientific calculator. If you need to borrow a scientific calculator, I'm happy to lend you one over the weekend. Just see me after class. Yeah, so I don't need anybody to go out and buy a new calculator. Yeah, Abacus is good, yes. Any other questions on the quiz? All right, so we'll give this out at the end of class. A graphing abacus? All right, so again, on page 38, one of my favorite apps when I learned of its existence was a slide rule app, which is just like really merging the defunct slide rule technology with the phones that we have now. All right, daily summary. Let us start in back with Elia. Can you read the daily summary? Yes, all the way in the back. Elia. All right, Elia, thank you. Thank you. Len, number 1. Okay, so integral from 1 to 3 of 8x cubed dx. It is an area of something. What's the curve we should be drawing? It is 8x cubed, a cubic, so we're going to draw 8x cubed, and it's going to look an awful lot like x cubed. It should be maybe steeper, stretched vertically. And the area in question is from where to where? It's from 1 to 3. So we're drawing vertical lines at x equals 1, and then another vertical line at x equals 3. And that shaded area is what the integral represents, right? Now, up until now, if we wanted to actually find that area, we would need to use the graphing calculator, right? We would type this into the calculator. The only ones that we could do by hand were ones with straight lines where we could draw like rectangles and trapezoids. Maybe we could do some circle stuff. So number 2 says instead of using the graphing calculator, we're going to tackle it by hand, and we're going to use our favorite theorem, the fundamental theorem of calculus. I've provided the left-hand side. Can you fill in the right-hand side? On the right-hand side, does it involve F or F prime? F. And in fact, 2 different F's. Which number goes first? B, top one, bottom one. What symbol goes between? Minus. All right, so there's our fundamental theorem. So in the example that we were looking at with this 8x cubed, what we're thinking of is that 8x cubed is the derivative of some function. I don't know what that function is, but it is the derivative of some function. And if I knew what that function f was, then I would just do f of 3 minus f of 1. You see, that's the fundamental theorem, right? So this problem really boils down to finding a function whose derivative is 8x cubed. And said another way, can you find an antiderivative of 8x cubed? Someone whose derivative is 8x cubed. Okay, so we can get there maybe intuitively, and then we'll have some rules pretty soon. If you took the derivative of something and you ended up with an x cubed, probably what did you start with? An x to the 4th, right? So it feels like an x to the 4th of some flavor is the right thing, right? Because the derivative of that would be 4x cubed. Then? That's right. Everybody hear the explanation? Put a 2 in there, knowing full well the 4 is about to come down, and you're trying to build an 8. 2 is exactly the number that will do it. Okay, so 2x to the 4th is an antiderivative. And now we're going to look at some notation. So here it is. The original problem was this. We are then going to take the number 3 and the number 1 and plug them into this thing and subtract, yes? So 2 times 3 to the 4th, 2 times 1 to the 4th, and subtract. So that will look quite familiar. It's right here. That's the f of 3 minus f of 1 part. But the new piece is highlighted here in the middle. That's our notation that says, okay, we just found the antiderivative. It's 2x to the 4th. And what we want to do is plug in the top number and the bottom number and subtract. And the compact way that mathematicians have come up with to say all of that is highlighted there. So you write the function, some brackets around it, x equals the top number, x equals the bottom number, all at the far right. Exactly. Top number of the function minus the bottom number. Kevin.
The last class we were doing that.
We're going to come to that in just a moment. Good question. Yes, it's equivalent to saying f of 3 minus f of 1. Right. Okay, so in this case, I mean, the number isn't super interesting. 162 minus 2 is 160. That is the area. What's interesting is that we didn't need a calculator to find it. We were just able to find the area of a very strange curvy region by hand. That's a surprising thing. You think about how limited we are in terms of shapes that we know the area of. We got like rectangles and triangles, squares, trapezoids, circles. I'm running out. Do you guys know anything I don't know? I know an ellipse area formula. Maybe some of you know that one. It's short and sweet is a list of things that we can do by hand until now. Turns out if we can find an antiderivative, we can find the area of all kinds of crazy looking curves. Okay, so let's take a look at number 4. Kevin, could you read 4?
What's another antiderivative for f prime?
Okay, so this was Kevin's question. So we said 2x to the 4th. Could we have picked a different antiderivative? 2x to the 4th plus 10 is another perfectly good one, right? Plus c is that general family of antiderivatives. So what if we use this? Would we get a different answer? I sure hope not, because the area has not changed. It should be 160 no matter how we do this problem. So if we did it this way, I'll just write the highlights real quick. What we should be doing is f of 3 minus f of 1, right? So f of 3 now is 2 times 3 to the 4th plus 10, yes? And then minus, and then f of 1, 2 times 1 to the 4th plus 10. And those 10s cancel. Right? So we're not finding the area of this moving up and down curve. We're finding the area of that fixed curve, the 8x cubed. And the way that we find that area involves an antiderivative, and there's a whole collection of these antiderivatives we could find. But when you subtract the one function value minus the other one, whatever constant you decided to put there is just going to cancel anyway. And so the most common thing for us to do is to just put the number 0. Okay, let's go back to Levi for 5. That. Okay, so the integral of 8x cubed dx is 2x to the 4th plus c. That symbol is a brand new symbol for us, that integral sign. Don't be fooled. It looks familiar. Looks quite like another symbol we saw earlier on this page, right? But what's the difference? There's no numbers on that symbol. It's a completely different symbol. Now we use the similar looking symbol because we want to talk about finding antiderivatives, and apparently finding areas is fundamentally related to antiderivatives. But that is a brand new symbol, okay? It doesn't mean find area. It means find an antiderivative.
Why didn't they just reverse it?
But it's clear enough, right? If there's no numbers on there, it's something different. All right, Rich is going to redefine the symbol, and he's going to bring a new one into vogue, reversed. Okay, and not just find any old antiderivative, but as Kevin says, there's a lot, find the general antiderivative, okay? So that symbol with no numbers means find the general antiderivative with that plus c at the end. So let's try number 6 here, and the process of finding antiderivatives is called integrating. It's an integral symbol, we integrate. Okay, so integral 2x plus 3 dx. That symbol used to mean area. This is a different symbol. What does it mean? Antiderivative. Doesn't say anything about areas. Okay, so 2x, where did it come from? X squared, that one's pretty straightforward. Then I see that plus 3. What was that the derivative of? Is 3x. But we are looking not for any antiderivative, but the most general one we can find, plus c. So there's our answer. Okay. No plugging numbers into the top and bottom and subtracting. Just find antiderivative, tack on the plus c, and stop. Questions? Lynn?
We have a expert a to the power r.
They will cancel out. We're going to have that rule on the next page, but for right now, we just kind of intuited, what did somebody take a derivative of to get 2x? Oh, it was x squared. We just, but you're right, there are rules that we'll see on. That 2 will still be in the problem, and it's going to cancel with the 1/2 that you're envisioning. Okay, we'll see it on the next page. Okay, let's go to 7. I'll do this one. Vocabulary associated with integral notation. The entire left-hand side of this equation here is called an integral. And then, I don't know, there's arrows, so I don't really need to point, right? You've got the integrand is the stuff inside, just like a radicand. Where do you see a radicand? Is the stuff inside the radical. So the stuff inside the integral is the integrand. That symbol, which looks familiar, is an integral sign or an integral symbol. The dx tells you that the variable is x, because just as well, this could have been 2a plus 3 and dA. And that second thing, the thing after the d, tells you what the variable is. Usually it'll be x or t. And then we found the kind of like normal, the simplest antiderivative, x squared plus 3x, and then we tacked on here this constant of integration. That's what we call that plus c, okay? All right, and then that entire equation you can read out loud. The integral of 2x plus 3 dx is, or equals, x squared plus 3x plus c. Okay, number 8, let's go to Zach. Thank you, Seamus. See what I did there with the C? Isn't that clever? Thank you. All right, number 9. Let's go to Elia. All right, let's move on to 10. So here are some basic formulas that are on this reference sheet on the first page of the packet. So let's kind of figure them out here. Basic power rule is what Len was referencing a moment ago. Somebody took a derivative and got x to the n. What did they take a derivative of? Was it x to the n minus 1? No, it's x to the n plus 1, right? Because they subtracted 1 from the power and it came down to an n. So it's x to the n plus 1. Now, if I just left that as my answer, we could check it. We could take a derivative and see if we get the x to the n that we want. Okay, so what comes down? N plus 1, and then times the x, and then what's the new power? Is n. So I got the x to the n part, but I've got this n plus 1 in the front that I didn't really want. So knowing ahead of time that there's going to be this extra factor of n plus 1, we need to kill it before it exists, right? N is just a constant. So that constant right there, when you take the derivative of that whole thing now, you don't need a quotient rule. The n plus 1 is just a constant. And it's just going to live there when you take a derivative. Just a quick example. Let's do like integral x to the 5th dx. Let's just apply the formula, then we'll check it. Let's see. So it says n plus 1, so the new power should be 6, and then we divide by that same thing, not the 5, but the new guy, the 6, and then we'll put a plus c. So if this is right, then when we take a derivative of the right-hand side, what should we get? We should get x to the 5th back. That's how you can check any of these. So when you take a derivative of this, okay, that's 6th, I'm just going to call a 1/6, just a constant. And then what's the derivative of the x to the 6th? 6x to the 5th. And then that 6 that comes down, we ahead of time got rid of it by putting that 1/6 there. So in fact, we get right back to the x to the 5th. So that's what this divide by n plus 1 is accomplishing. Okay, we're going to use that power rule so often I say let's also do it in words. So then this power rule for antiderivative says add 1 to the power. And divide by the original power or the new power? By the new power. I will say that phrase many times. Add 1 to the power, divide by the new power. Okay, what about this one on the top right? Integral of 1 over x. Somebody took a derivative of something and they got 1 over x. It's ln of x, which is completely out of left field. And, you know, if you don't know what to expect, it's just like what happened. But you can check by taking the derivative. What's the derivative of ln of x? Is 1 over x. Perfect. Len? We're going to bring the absolute value in. I think we're not going to talk about it for right now. But yes, we will make it more correct soon enough. Okay, the next one, this will be your favorite one, the integral antiderivative of e to the x. E to the x, perfect. Don't forget these plus c's. All right, a to the x is not going to be as friendly. I'm just going to copy it like it was, a to the x. That seems reasonable. But what's the derivative of a to the x? It's got this extra factor that pops out. Is an ln of a, the number, not the x. But times ln of a is what pops out when you take a derivative. Knowing that, what do we have to do ahead of time? Is we have to divide by that ln of a so that it disappears when it pops out. All right, cosine and sine. They're really easy to get them wrong because the derivatives just swap back and forth, but some of them are negative and some of them are positive. Who has a derivative of cosine? Sine, just plain old sine. So sine of x plus c. Whose derivative is sine? Okay, well, I'm going to put the natural choice, which is cosine. But if you take a derivative of cosine, what do you get? Negative sine, and I didn't want negative sine. I wanted just plain sine, so we need to put in, and divide by -1 if you want, but put in an extra negative ahead of time to cancel the one that pops out. Okay, and then these last two are kind of more general. When you take the derivative of the sum of two functions, life is good, right? You get to just completely separate these two guys, take their derivatives, and then add them at the end. Well, when you're doing antiderivatives, it works just as nicely because it's just the opposite process. So I guess what we should be able to do is take the antiderivative of f, and then completely separately take the antiderivative of g, and do what in the middle is add them up. And there's a subtraction possibility as well. Because it's nice for derivatives, it's also nice for integrals. If you are taking the derivative of the product of two functions, is that as straightforward as this? No. So we are not going to be able to put something like the integral of f times the integral of g. It's not going to work that way. We'll see what we get to put. If you do the quotient derivative, is that nice? Not so nice. So we're not going to put anything there either. But as we saw up above with this example, constant multiples stay when you take derivatives. So constant multiples stay when you take antiderivatives. Symbolically, we can just think of taking that c and bringing it outside. Just worry about the regular antiderivative of f and then multiply it by c at the end. There is a product rule for integrals, which we will see. Not today. Oh, that reminds me. Brendan and company pointed out that one of my problems here, this was on the syllabus, it's either the back of the syllabus or that separate page that I handed out when the calendar changed. I don't know if you want to change it, but do you see down here, right there in class number 7, I have 4E. This is updated and this is correct right now, but for you guys, I think 4E is in class 3. 2 or 3. So I accidentally put 4E before it should have been fair game. So if you are using these practice problems to prepare for this quiz before you take it this weekend, don't worry about 4E. Right? Make a note if you want to, but just want to put out there, we don't have the tools yet to solve 4E. That's going to go in class 7. Okay. All right, so let's take a look at this complicated looking integral antiderivative problem. So the first thing we have to do is decide fundamentally what is this, and what this is a subtraction and an addition, right? And are those things nice as far as antiderivatives are concerned? Yes, they are. So I'm going to write out a step that, like after today, I'm not going to be writing out anymore, but let's write it out here. We can do the antiderivative of 2/5 e to the x dx, and then a completely separate integral, 3/4 x to the e dx. And this is so much fun, we'll do it one more time. Integral x minus 1 over square root of x dx. With what symbols in between? A minus and then a plus. So I know it's a lot to copy down, but don't get lost in the copying and then forget to think about what's happening. This is something very basic, right? Because derivatives work well for addition and subtraction, and you can completely separate them in your minds, do the same thing for antiderivatives. Sephora. The plus c is going to come in at the very end because we haven't actually done any antiderivatives yet, but once we start doing them, we'll tack on 1 plus c at the end. Is that your question? We'll talk about it. Okay. This is correct as it is. The plus c, on which one? This one? Yeah, so the reason we don't need to tack on the plus c is because the integral sign is still here waiting to be done. And when you do that antiderivative is when the plus c comes in. So if that symbol, integral symbol is still there, we don't need to put it because we haven't done the antiderivative yet. Okay, equals. All right, that 2/5 is a constant multiple times some function. What can we do with constant multiples inside of integrals? We can pull them outside. So this is 2/5 times the integral e to the x dx minus 3/4 integral of x to the e. And then, okay, so this guy we'll have to deal with in kind of a different way, but is everybody okay pulling those constants out? The goal is to take the integrand, remember that's the thing inside the integral sign, and make it simpler. Make it something we can manage. And so every step of the way, we've made that integrand simpler. Okay, this x minus 1 over the square root of x, that looks really complicated. It involves division, and none of the rules, we've got like 8 rules up above here, none of them have division in them. So somehow there must be a way for us to rewrite this that doesn't involve division. So how about we take that guy and rewrite it as x minus 1 over x to a power, just changing the square root into x to the half. Yeah, all right, so let's do them piece by piece here. Let's start at the far left. Okay, equals 2/5, hanging around, times. Now we're finally ready to do an antiderivative. What is the antiderivative of e to the x? E to the x, that's one of our, like, we only know 6 antiderivatives at this point. That's one of them. Okay, technically there should be a what that we stick on next before we look at the next. Technically that plus c. But I think Alex was kind of getting around this, is that instead of putting a plus c and then a plus d and then a plus f or something like that, we'll just say we're going to have 3 constants popping out, and if you add 3 constants, you just get a constant, which we're going to magically call plus c, right? Okay, this next one, minus 3/4. X to the e is one of the 6 things in our list. It is x to a number, isn't it? Don't get distracted by the fact that it's a special number. That is just x to a power. And our rule in English said you add 1 to the power and divide by the new power. So x to the what power? E plus 1 divided by the new power, e plus 1. There you go. Right? Notice how different these antiderivatives were compared to how similar the original integrands were, e to the x and x to the e. You treat them completely differently. They are fundamentally different kinds of functions. Right. Okay, this guy still needs work. I still can't deal with division. So how about we do some algebra here? I'm going to make use of the fact that I can split this fraction up into 2 fractions with a minus in between. What's my first fraction? X over x to the half minus, everybody comfortable with that? Split it up into 2 fractions. And you can distribute the x to the 1/2. Essentially, it's the same as what we're doing here. Okay, there is a symbol missing. What symbol is missing? It's not the plus c yet. It's a dx, because you cannot have an integral sign without a d something. And for the first time, there's actually one more symbol missing. Because our integrand is kind of complicated, we need to throw it in parentheses, which is our way of saying the dx applies to everything, kind of distributes into everything. Okay, we are almost there. One more step of algebra, and then it's calculus time. Plus integral. Okay, what do we do with the powers in the first fraction? Trying to combine these guys. Is it 3/2 or is it 1/2? Right, we subtract the powers, right? This is not a calculus thing. This is a combine those x's thing. So when we subtract the powers, we just get plain x to the half minus. Okay, again, I can't handle a fraction, so I need to bring that x upstairs. Again, it's not a calculus thing. What's the new power? It's just the negative of what it used to be, right? So that's bringing it upstairs. All right, and then finally, we have things that we can find antiderivatives of. I see a subtraction sign. I say that's fantastic, because in my mind, I can just separate. Antiderivative of x to the half. This is our power rule. What do we do with that power? We add 1 to that power and then divide by the new power. Okay, so plus x to the 3/2 divided by the new power is 3/2 minus, same game with the other guy, add 1 to the power, it becomes 1/2 divided by 1/2, that new power. And now that we've done all our antiderivatives with this one thing we've been holding in our pocket, is that plus c finally make its appearance. Okay, and so I think we're ready for our final answer. I've been kind of lazy in not copying those guys down, so we're going to bring them down in our final answer. So we go 2/5 e to the x minus 3/4 xe plus 1 divided by e plus 1. And then finally, we should clean up this division of a fraction, right? Instead of dividing by 3/2, it's the same as multiplying by 2/3. So we're going to write that as a 2/3 times x to the 3/2. Dividing by half is the same as multiplying by 2, so 2x to the half. Yeah, and you could change it into radicals if you want. Okay, so I'll raise this up. And that is our final answer. Questions on that? Now, like I mentioned before, after today, I'm not going to ask you to really separate and do as much detail as we did here, right? We separated this subtraction and addition into 3 different integrals, and I'm going to ask you to do that in the activity in just a minute. But after today, and even starting on tonight's homework, I'm not going to ask you to do that anymore. Just in your mind, say, okay, I'm just separating these in my head, and I'm going to do my antiderivatives. Oh, Steve. They're, we do. Anytime there's an addition or a subtraction, we require parentheses. Yeah. Okay, so last thing and then the activity. Number 12, our next reader, we did this table. Let's come up here to Rob. Okay, so integral of x times sine of x. What makes that hard? It's multiplication, right? You can't separate it because we can't separate multiplication when we're doing derivatives. So we just can't do it here either. This is Elia's question. We will learn how to solve this problem. There is a product rule version of antiderivatives, but we can't do it just yet. This next one, xe to the minus x squared. Again, it is a product. You cannot separate unless it's addition or subtraction. What kinds of products can you separate? Well, not really separate, but what kind of thing can you take out if it's a product? It's a constant, right? We took constants out of integrals, no problem. But that x is the end of the ballgame. You cannot take an x outside of an integral. We will learn how to solve that one pretty soon too. And then this one, which actually looks even nicer than this one, right? It's the same, but with one fewer thing to worry about. Okay, so it turns out this one is pretty easy, and we'll see it in like a couple of weeks. And this one, I don't believe anybody has ever found an antiderivative of that. Yeah, the middle guy, we're gonna do an opposite of a chain rule kind of thing. But the last guy, I don't believe has any simple antiderivative. It's hard to answer the question. It's a great question. What makes the last one difficult before we see why the middle one is easy? So you're gonna have to hold that thought. We can, and the chain rule is either going to make it work, like in this case, because you have the extra piece that you need, or it's going to make it fail because we don't. So we're going to come back to your question, Sephora, but not until we see why this one is easy. Okay. It will, I promise. All right, activity starts on the next page. You are doing 3 things for each of these integrals. You are finding an antiderivative for the integrand. Notice that each of these guys has limits of integration, right? So we're going to be doing these ones without the calculator, and that means finding antiderivatives of each of the integrands. And then we're going to use that fundamental theorem of calculus, focus on the good notation we talked about. You should have something that you're going to fill in there, and then plug in the 3 and plug in the -3 and subtract. And then finally, after you've done all that in part C, you're going to use the calculator and compare to your answer in part A. And we really, really hope that they are the same answer. Raise the flag if I can help.